Hello everyone, welcome back. Today we'll be covering TCP versus UDP. These are the protocol. We'll be covering port number in a separate video because it deserves a separate separate video, and it has a bit more complex concept to understand, so it is better to cover that in the next video. So today we'll be focusing on what is TCP and what is UDP. So TCP stands for Transmission Control Protocol. So it is a connection oriented protocol. It's like a certified letter with a return receipt requested. It guarantees delivery, track orders, and manage congestion, but it has overhead. So UDP, it is a connectionless. It's like throwing postcard in mail. It's fast, efficient, and lightweight, but it doesn't care if the packet gets lost or arrives out of order. So in order to just understand in a simple term, then TCP, it is a connection oriented. It has a path, so it is guaranteed to transfer your message or your data to the desired destination. But with UDP, it is fast, it is efficient, it is lightweight, but it doesn't guarantee that your data will be is guaranteed to be delivered to a desired destination. So that is the difference between them. So as you can see, sender in TCP, there is sender and receiver, right? So sender, this is basically a three-way handshake. We'll discuss that in our next in a few minutes, right? It establishes a three-way handshake which forces it to become a connection oriented. That is the reason it is guaranteed to deliver your message. But in UDP, as you can see, when receiver request anything from the sender just responds, right? It sends response and a data, and that's it. It doesn't have the it doesn't have the confirmation that the message is sent correctly, in order, or is secure. So that is basically what UDP and TCP has a major difference in. So let's look at the three-way handshake. So this is the reason our TCP is connection oriented, right? So before TCP can send a single byte of actual data, it must establish a reliable virtual connection using a synchronization exchange of flag. So basically we are gonna use flag in order to maintain a handshake. It is done before you send a data. So what happens is we have a client, right? And we have a server, and first client sends a synchronization to a server. So synchronization is basically a flag. So what it means is, so the client sends an initial sequence number as well. So we'll discuss that later on in detail. So just for time being, understand that client sends initial request number and sends a synchronization flag, right, and sends a packet to our server. So it says, hey, I want to talk to you in a so what it basically means in our human language is, hey, I want to talk to you on port 80. This is my starting number. So starting number is our initial sequence number. Another is server sends back a synchronization acknowledgement flag. Okay, so the server receives it, it acknowledges the client number, selects its own starting number, a random number, and sends back the packet with both synchronization and acknowledgement flag. In our human language, it basically means server says to the client, I hear you, I acknowledge your number, this is my starting number, let's connect. So basically they're trying to establish a connection, right? So again, client sends an acknowledgement flag, the client receives the server response and sends a final packet with the acknowledgement flag, said got it, connection established, let's send the data. So this is how the connection is established. Okay, this is the figure. So basically what we know is, this is a client, right, and this is a server. So client sends a synchronization with a initial sequence number, right? So initial sequence number, and once the client sends a synchronization flag with initial sequence number, our server responds back with synchronization and acknowledgement flag, right? So it sends with this, and again with that it sends an initial its own initial sequence number in order to establish a connection. And once it establishes a connection, client sends an acknowledgement flag. It says let's connect, and after this, then only a data is transferred, data transformation transition happens. So this makes a TCP connection oriented, and this is the reason it guarantees data transformation to a desired destination. So this is the reason. Now, so what is initial sequence number, right? As we discussed, initial sequence number was used over here. It was used over here with along with the packets and a synchronization flag. So what is initial sequence number and why do we need them? Okay, so an initial sequence number is a unique 32-bit random number assigned to the first byte of a data in a new TCP session. Okay, established during the TCP three-way handshake. Obviously, both the client and server generates and exchange their own random initial sequence number. So why is it used? So first is data ordering. It provides a starting reference point so that the receiver can track, order, and reassembles incoming data packet correctly. Another reason is security and prevention. Modern operating system randomizes the initial sequence number for every new connection to prevent hacker from predicting sequence number, which protects against malicious session hijacking and data injection. So let's deep dive into more about this. So why not only send the data in a flags during the three-way handshake, right? So why do we need initial sequence number in the first place? So to understand that, we have to look at how physically internet actually works. The internet is stateless, as we know, and it is lousy. It does not guarantee that the packet will arrive in order, or does it? So assume here is an actually why sending raw data with an internet sequence number is impossible. So first, what happens is, imagine you have a large number of 50 MB file, right? Because of a internet limit. So let's do that with an example. Okay, so sorry, yeah. Let's do with this one. Okay, first let's visualize and this only. Okay, so basically assume that we have a large amount of, so this is an 50, oh my bad, so let's assume this we have a 50 MB large file. So this we have a 50 MB large file, right? So you want to transfer this to say a PC. So you want to transfer this to a PC. Okay, so this is a PC. So this you want to send this to this is our destination. Okay, so this is our destination. So when you so you cannot send this giant chunk of a 50 MB of a file in a one you can't send that. So you have to chop it into a 1000 tiny packets. So if you send a raw data packet without any numbering system, right? So if you do that, so what happens is, if you do that, right? So if you do that, so assume your when you divided a packet into 1000 pieces, right? So assume your packet 1. So basically your packet 1 is it is going through an fiber optical cable, and your packet 2 is going from a router which is in the next city, and your packet 3 is going from it might arrive before your packet 3, right? I mean, sorry, packet 2. So when these without any sequence number, so when these all go to the destination, right? So your order becomes P1, P3 and P2. So your order becomes this, and your file becomes corrupted. Your 50 MB file, which was supposed to go in an order, it becomes corrupted. So that's basically what happens. And if we use a sequence number, it's like a page book in your is a page number of your book. Without page number, a dropped stack paper is ruined forever. So what happens if you use sequence number is your packet go in a sequence order, which helps receiver to receive a file in an ordered way, in a manageable way. So now, why do we need an initial right? So why do we need an initial number? First of all, why not just start at 0, at 1, right? So if so what happens is a network suffers from a delay duplicate. So what happens is delay duplicate is you have a connection 1, right? So this is your connection 1. You connect to a server. So you start at packet 1. right? You send packet 1, 2, 3 respectively, you send that, and packet 2 gets stuck in a congested router loop somewhere in the world. The server never gets it, so your connection times out and closes, right? And after some times a connection 2 is established, connection B established, you instantly open a brand new connection to the same server. Instead of packet 1, again you send data, you send packet 1 in connection 2, you send packet 1, packet 2, and similarly packet 3, you send bunch of packets, right? After that your ghost packet arrives. So basically right after you send a new packet which is of a connection 1, packet 1, and old packet 2 which was from connection 1 now is finally released and finally escapes the traffic jam and arrives at the packet. So because connection 2 also started at 1 and server thinks this old ghostly packet 2 arrives is a part of your new data, it inserts a dead data into a new file. So basically your whole file becomes corrupted. So that is basically what happens if you use an initial number always starting from 1 in every new session. So to fix that, connection A starts at a random number like 5000, right? So connection B starts at a random number like say 900,000. So if the old packet 2 label sequence as 5002, right, so arrives during a connection 2 like it did over here, then the server looks at it and says we are currently at 900,000 range. The 5002 packet is an ancient history and it immediately throws out of it. So that is basically why initial number ISN doesn't start at 1. So how does the receiver know ISN is truly random, right? The receiver does not know, it doesn't care. Actually, the receiver has no requirement or mechanism to audit how random the number is. The randomness is entirely defenseless. So the receiver only job is to, when the sender says my starting number is 4321, right, the receiver simply accepts the truth and it records 4321 in the memory. So and the math is, if the baseline is 4321, then the receiver expects the next data to be 4322. So it basically accepts that. So this will be our packet 2 and it doesn't care why the sender picked 4321. It just uses it as the starting line of the counter. So why we use each protocol like TCP and UDP, right? So TCP it is used when data integrity matters, when the security concern is high. If losing a single bit breaks the file, you must use TCP. Like web browsing, HTTP is missing bits means corrupt code or broken image. File transform, FTP or missing chunk corrupts the archive, right? SSH remote control drop command would break your system configuration. Email message cannot arrive with a missing text. So you use UDP when you need speed and reliable time, performance matter. So if waiting for a retransmitted packet causes lag or stuttering, packet dropped are acceptable. So when live video calling, right, if a packet drops during a video call, it is better to experience a minor half-second glitch than to freeze. That's why when you are in a video call and it glitches, you won't understand what your friend, if you're talking to a friend, if you're in a video call, then you won't know what your friend has just picked if you're glitching. So that is basically why. So because live video streaming uses a UDP protocol. So that is why online gaming, so it is test synchronization must happen in a real time and old position packet is useless. And DNS and DHCP, so queries must be incredibly fast and lightweight. If a DNS query get lost, the client just retries. So that is basically why DNS uses UDP. So these are some of the questions that can be asked in a Viva or interview. So why is SYN, which is a flag, flawed attack? What is SYN flag synchronization flawed attack, and how do you protect against it? So a type of a denial of service. So attack where an attacker sends thousands of a synchronization packet with a spoofed source IP address. The server responds with a synchronization acknowledgement flag and allocates memory space waiting for the final acknowledgement, which never arrives. So the server runs out of the resources and crashes. So in order to fix them, as a system admin, you mitigate this by enabling a synchronization cookie on the OS 5 level, which avoids allocating memory state until the final acknowledgement arrives, or reducing the connection timeout parameter. So basically enabling synchronization cookies and only allow allocate memory until the final synchronization allows for every synchronization flag. Another is why does TCP reliably handle packet loss during how does TCP reliably handle packet loss during data transfer after the initial handshake is completed. So through sequence number and acknowledgement, if a client sends a packet 1 to 3 but packet 2 gets dropped, right, the server will send an acknowledgement back indicating it is still waiting for packet 2. The client notices the missing acknowledgement and retransmits packet 2 automatically. So this is how it is done. Another is why does DNS uses UDP instead of TCP? Again, so overhead reduction, simple. A TCP connection requires a three-way handshake, right, before sending a request packet 1 and receiving the answer plus a teardown total of 7 packets. So UDP does it in exactly 2 packets, like request and response, right? So multiplying that by billion of queries globally every second, the TCP would completely choke the entire infrastructure. So basically congestion would happen. So that's why DNS prefer UDP over a TCP. So where in TCP 7 packets, a total of 7 packets in order to establish the connection, 7 packets is needed, whereas in UDP only with exactly 2 packets the whole thing happens, and it needs to happen in a millisecond. So that's why DNS prefer UDP instead of TCP. So this much for today. So I hope you guys understood why difference between TCP and UDP. So in next video we'll be covering port number. We'll be covering a bunch of commonly used port number, why it is used, where it is used, and where the problem occurs. So I hope you guys learned about TCP and UDP. I'll see you in the next video. Thank you.